page 560. And got it? Do I have the right thing? Ah, yes, the second derivative of parametric equations. Always throws people off. Okay, so for 10, we've got
Is that supposed to be 37 or 27 up there?
37. And we're finding it at t equals 2. Okay, so for the second derivative, we need the first derivative. So I'm basically going to do part A as well. So for part A, you take the derivative of this. That is positive 3 times t to the negative 2. You okay with that? Okay, then dx dt is negative 2 times t to the negative 3. So then dy dx is that dy dt divided by this dx dt. So 3t to the negative 2 divided by negative 2t to the negative 3. So then you could subtract the exponents. Negative 2 minus negative 3 is positive 1. So this is negative 3 halves t. So that's dy dx. Okay, so then for part B, we're taking the second derivative. And how you do the second derivative is you take the derivative of this, dy dx, which is negative 3 halves. And you put that over dx dt, which is this. That's the second derivative. So what we're looking at is d squared y dx squared, aka the second derivative. So then that'll divide out to 3/4 t cubed, if I did that right. So the thing that always throws people off, Cassie, is they feel that they should be doing the derivative of this divided by the derivative of that for the second derivative. And that's just not what it is. It's the derivative of dy dx, which is weird, over just the first dx dt. That's just what the formula is. I mean, we could get into theory about why that is, but today's not the day to do that. Good. Is everybody okay with 10? Yes, Dan? Yes, I'm ready.
Alright, can you do 21D?
Already did it.
You said the C though.
Sorry, it's in a different place. It's all good. It's all good. But later today, if you watch the video from Second Bell and you still have a question about it, I'm totally open to answering that question. Yes?
Can we do number 11?
Sure. So this is page 430, number 11. And we've got y equals sine of x. So that looks like this. And we've got y equals x, which, believe it or not, is above y equals sine of x. So I'm going to exaggerate that just for effect. So there's the line y equals x. It probably wouldn't be that steep, but so we can see that there's space in there, I'm making it extra steep. And then x equals pi over 4 is right there. So there's our shaded region. So what throws people off on this problem is they can't believe that the y equals x, because when you graph it in your calculator, it looks like it's kind of on top of y equals sine of x. So they can't believe that it's above it. So that's why I exaggerated it there. So then we're just finding the area of that. So that's the integral from 0 to pi over 4 of x minus sine of x dx. Totally good? All right. What's next? Yes?
BC 49A.
I think not. Did I just assign C or something, or
48A and C.
48A and C, but not 49A? Maybe you misread the 48AC. So yeah, we don't know how to do 49A yet. And you didn't have to do it, so. Yes?
Do we know where 13 are, BC?
Yeah, so page 560, number 13. So part A is horizontal tangents, and that's when the dy dt is 0, but the dx dt is not 0. So dy dt is 2 cosine of t times negative sine of t. You okay with that derivative? So the cosine is being squared, so I brought the 2 out front. And then cosine is now to the first power, because I subtracted 1 from the exponent. And then but it was a chain rule problem, because cosine was sitting inside of the square. So I had to multiply by the derivative of the cosine, which is negative sine. Okay, so there's dy dt, and then dx dt is, the derivative of cosine is negative sine, so that's going to come out to positive sine of t. Okay, so now for horizontal tangents, I need this to be 0, but that not to be 0. So I'll set the dy dt equal to 0. And that happens when either the cosine is 0 or the sine is 0. But all of these answers make dx dt 0. So they're not horizontal tangents. Only these are horizontal tangents because they make dy dt 0 and also not dx dt. Okay, so those answers are pi over 2 and 3 pi over 2 and 5 pi over 2, et cetera, et cetera. Does it have a range that it gave us? Well, it says find the points, so I bet that this starts repeating itself after a while. You get the idea, right? Okay, so now to find the point, we have to plug pi over 2 back into the original formula. So that's, for x, it's negative cosine of pi over 2. Cosine of pi over 2 is 0, as we just discussed. So that x value is 0. And then y of pi over 2 is that cosine squared. Yes. So cosine of pi over 2 squared, which is 0. So there's a horizontal tangent at the point 0, 0. Now let's see what happens with 3 pi over 2. Maybe there's a different point. So 3 pi over 2 plugged into the x equation is the negative cosine of 3 pi over 2. Cosine of 3 pi over 2 is also 0. So that's going to come out to 0. So it's not going to be a different point, because when you take y, that's still going to be 0 as well. So there's only one place where there's a horizontal tangent at 0, 0. Okay, so now for part B, we're looking at vertical tangents. Vertical tangents happen when this is 0, but that's not 0. But whenever this is 0, that's going to be 0. So there are no vertical tangents. Okay. What's next? Yes, Dan?
38.
38, good, that one's golden. So this is page 430, number 38. And it says find the fluid force on the base and each side. So I'm going to start with the front side. So the front of this olive oil can is rectangular. And it's your pick as to whether this is 3.5 or whether this is 5.75. It's not really labeled. But to me, it kind of looks like the one in the front is shorter than the one going back. It's not a big deal, though. So I'm going to pretend that the front is 3.5. And then the height is 10, right? So we're trying to find the fluid force on that front of that can. Okay, so what we need is olive oil weighs 57 pounds per cubic foot. So we need to multiply that by the depth to get how many pounds per square foot of pressure there is at a certain depth. But the problem is the depth keeps changing, right? This part of it is at a different depth than that part, which is at a different depth than that part. So we need a variable for our depth. So we usually called it y. So then you take 57 times y, and that's the number of pounds per square foot that is felt at that depth. Feeling okay? Okay, now you need to multiply by the area to get the number of pounds. The area at that depth is pretty tiny. And so it's just the area of that rectangle, which is 3.5 dy. So this is the number of pounds of pressure that is experienced by this little bit of the front of the can. So then we need to add the pressure felt by the bit under that, and all the bits stacked on top of it. So we're going to add up all those pressures. Sorry, all those poundages. And the depth goes from 0 to 10. So then you would just take 3.5 times 57. Yes?
The height inches. So
Yes, thank you very much. So I need to convert this to feet. So that would be 10 twelfths, and this would be 3.5 twelfths of a foot. Thank you so much, Caleb. So basically 10 inches is 10 twelfths of a foot, and 3.5 inches is 3.5 twelfths of a foot. Totally okay with that? Okay, so then the rectangular shape on the side is going to be exactly the same, except instead of 3.5 there, we're going to have 5.75 there. that's how you do the two sides, the right side and the left side. And then finally the base. So the very bottom of the can. The entire base is at the same depth. The entire thing is 10 inches underneath. So you just have to take your 57 times 10/12 to get the pressure that is felt at that depth. And then you just multiply by the area of the bottom rectangle, which is 3.5 times 5.75. That's the area of the rectangle on the bottom, times the pressure felt at that depth will give you the number of pounds felt at that depth. Good. Sure you totally understand it. Not just I could do it next time, but I know what's going on. Okay, cool. Thanks, Dan. Yes?
53C.
I did all of 53 last period. Yes, Grace.
Video 55.
Yes. Just to help you visualize on 53C, Matt, shaded region looks like this, right? They said the base of a solid is, so this is the bottom of the solid. You cut it like this, you get squares. So. Okay. Okay, so 55D, is that what you said, Grace? I imagine you weren't very amused when you found out there were 4 parts to this question. It's an amusement park, so I'm trying to be funny. Okay, okay, so 55D. So at what time does the model predict that the number of people in the park is a maximum? Okay, so you can find out how many people entered the park by integrating E of t, right? Because E of t is the rate at which they enter. So the area under that is the number that entered. Okay, so the integral of E of t dt is the number of people that entered. And they opened at 9 a.m., right? So you want to integrate from 9 to whenever. So if you want to know how many people entered the park from 9 to 12, you would integrate E of t from 9 to 12. Or from 9 to 10 o'clock at night, you'd integrate from 9 to 22. 10 o'clock being 22 military time. Okay, so then that's how many people have entered. So then you want to subtract how many people have left, which is the integral of the L of t function. And you don't need plus c because at t equal 9, there's nobody in there. So in that, that's plus 0. Now in the penguin problem last week, we had to plus 100,000 to this, right? So this is a lot like the penguin problem.
Yeah, I remember that. I just.
Yes, no, it's totally fine. I'm not saying you should have remembered it. Now I'm just triggering your memory. Okay, so this is P of X standing for number of people in the park, I guess. The number that entered minus the number that left. So if you want to know how many are in there at noon, you just put a 12 there and a 12 there. And then you got it. Okay, so then the question is, when is this function, when is the number of people the max? So you want to maximize this function. So to maximize a function, you take the derivative of it and set it equal to 0 and undefined, right? So we need to take the derivative of p. Well, the derivative of this is a piece of cake because the d dx just crosses this out, right? And crosses that out. So the p prime is e of x minus L of x. Okay, so then we need to set that equal to 0 and undefined. It's never undefined. So we just need to figure out when it's 0. And that happens when e of x is equal to L of x. So then you just put e of x in your y1 and L of x into your y2 and see where they intersect to solve that. You know what? It's possible to cross multiply that and also solve it quadratically as well. But I think this is all calculator active. Yeah. So whichever you want to do is fine. Let's see, we got 15,600 divided by, don't forget parentheses, divided by parentheses x squared minus 24x plus 160. And then 9890 divided by parentheses x squared minus 38x plus 370. The x window is easy, it's 9 to 24, right? The y window is a little bit trickier because you don't know how many people are going to be in this park, but probably thousands. So I'm guessing maybe 0 to 10,000, I don't know. Oh, this isn't the number of people in the park. This is the rate that we're graphing. So you don't know, we need to guess, we need to be thinking about for y, how fast people are running, like 100 per hour maybe. I didn't get a horrible window with 1,000 or with 10,000, but that was a little much. Looks like maybe 1,000 per hour is probably a little better. So then you calculate for that intersection point. Are you getting a decent graph?
Yeah.
I'll check you in just a second. 15.7984, yeah.
Yeah.
Okay, so x equals 15.794815. I don't want to round in the middle of problems, so that's why I'm putting so many decimals down. Okay, now this is a closed interval problem, right? It's 9 to 24. I think the park closes at midnight. Or no, 23. Closes at 11. So I would do it, I would figure out which was the max using the closed interval method. I mean, you could do the number line thing, right? And put your critical value there. And then if the slope is going up and down, then you find out that that's a local max. And since it's the only critical value, then it's the absolute max, right? But people forget about this closed interval method, so sometimes I like to do that as well. This is a specialized method. It only works when you have a closed interval, though. Okay, so this should be a 9. So we know how many people are in there at 9, right? Nobody. Did we have to figure out? No. Might as well do this right. So math, 9 to 15.794.815. You know, you can go to vars, yvars, y1 instead of typing that function in. Did you know that, Grace? So press vars over to yvars. Y1 is your entering function, right?
Yeah.
So that's what you integrate. Then minus math 9. And then vars, yvars, y2 for the other function. So there's 3,950 people in there. Is anybody else getting that number?
I have
Thank you. And then just type in 23. Don't retype it, right? Do second enter.
and it's 1,
One person left?
yeah.
That's a lonely person there. Security's going to spend 6 hours looking for that one person, right? So the max is obviously, what does it say? The maximum number of people in the park is 3,950.680. Turn this in, please. But you can come back and ask questions if you want. Non-calculator tomorrow.
I'm not gonna be here Tuesday, so I was wondering if you could send this someone on a.
Oh, I see how it is.
Yeah.
You voted for Tuesday, now you're
No, I voted for today.
Sure.
Would you like me to take it like info tomorrow?
Whatever's best for you.
Okay. Can I take it info tomorrow, or like, I also have study hall, like fifth bell.
Fifth would probably be quieter.
Okay. Okay, thank you.
Mr. Early,
Yeah.
what are you doing for the bell?
Answering questions.
Okay.
So you can stop by. It'll be good.
Well, like I'm stuck on a problem.
Yeah, that's fine.